A digital forensics lab operates as a highly regulated, secure evidence locker. Every procedural step is designed to preserve an unbroken chain of custody, ensuring that digital data remains legally admissible in a courtroom. The standard for this environment is dictated by the ANSI National Accreditation Board, or ANAB. They serve as the global authority that audits and accredits crime and forensics labs worldwide. To maintain ANAB accreditation, an organization must define its physical security protocols, quality assurance processes, and operational policies before any casework begins. The lab manager oversees this ecosystem, enforcing ethical standards among the staff, establishing quality assurance workflows, and maintaining the facility's physical and digital security. Processing digital evidence correctly requires a dual-layered fortress, where precise physical infrastructure protects digital integrity. If this physical and procedural perimeter fails, extracted digital data loses its value in the courtroom due to compromised integrity. This blueprint shows the baseline layout for a mid-size forensics lab, focusing on spatial containment and controlled access. True floor-to-ceiling walls and heavy-duty doors prevent unauthorized physical intrusion. Inside, evidence is stored in heavy-duty steel safes, and every entry is recorded in visitor logs. There are also invisible physical threats. Stray static electricity can corrupt an exposed hard drive, so labs require anti-static pads and rigorous cleaning schedules to eliminate dust buildup. Investigations involving national security or high-risk subjects often require Tempest-qualified facilities. Tempest standards mandate rooms shielded with grounded conductive metal to block electromagnetic radiation, or EMR, from leaking out or penetrating the facility. Because Tempest facilities are expensive to build and test, low-emanation workstations are frequently used as a cost-effective alternative. An unlogged visitor or a static discharge can destroy evidence viability. Rigorous physical maintenance is the foundation of the forensic process. In a regional lab setup, complex network topology relies on strict physical zoning to maintain evidence integrity. Notice the cluster of forensic workstations in the main secure area, compared to the Internet and Internet PCs, which are isolated near the exits. This setup enforces a strict lab rule. Internet-facing machines must never be connected to the forensic workstation network. This physical air gap protects the evidence from external hacking, malware infections, or unauthorized remote access attempts. Digital isolation establishes a defensible environment where data remains uncontaminated by external traffic. Inside that environment, the forensic workstation itself requires specialized architecture to handle large-scale data extraction. While standard PCs focus on balanced application performance, forensic workstations are engineered for extreme processing power and maximum storage capacity to hold multiple large disk images. Investigators must also maintain strict legacy compatibility. The workstation needs hardware interfaces like IDE and SCSI cables, along with older operating systems to analyze outdated devices recovered from the community. Certain workloads dictate hardware choices, particularly when decrypting suspect data using dictionary or brute force password attacks. These attacks work by checking lists of potential passwords or systematically running every possible character combination to find a matching value. To process combinations efficiently, investigators install multiple graphics processing units, or GPUs. This offloads intense calculations, keeping the primary CPU free for other tasks. A forensic workstation acts as a custom-engineered computational engine designed to manage extreme data loads without bottlenecks. With the hardware configured, investigators must account for how standard operating systems behave during data acquisition. By default, they constantly attempt to write metadata, such as access timestamps, to any connected drive. To prevent this permanent alteration of evidence, labs rely on a critical hardware failsafe, known to investigators as the write blocker. A hardware write blocker acts as a physical bridge between the suspect drive and the forensic PC, intercepting and blocking interrupt 13 write commands. While write commands are destroyed, read commands pass through cleanly, allowing the investigator to make a flawless copy without altering original data. While software write blockers exist to modify the Windows registry, hardware write blockers provide a physical barrier that is independent of the workstation's software configuration. Hardware-enforced immutability removes human error from the acquisition phase, providing proof that 0 bytes were altered during extraction. After the hardware layer acquires evidence, the software layer must validate it for judicial proceedings. The National Institute of Standards and Technology, or NIST, runs the Computer Forensics Tool Testing Program. They establish the criteria that software must meet to ensure the integrity of the analysis. The first critical metric is repeatability, the guarantee that a specific software tool produces the exact same result every time it is used on a dataset. The second metric is reproducibility, the guarantee that different software or hardware tools produce the exact same result on the same dataset. Using a hexadecimal disk editor, investigators can dive into the raw data to cross-verify the findings generated by automated graphical tools. To prove these datasets match, investigators use hashing algorithms like SHA-1. These algorithms generate a unique mathematical string from the data, providing evidence that the copies verified across different tools are identical. Cryptographic validation is the final filter. It translates acquired technical data into mathematically proven facts for the court. Maintaining this ecosystem requires constant administration and a strategy for handling the cost of lab operations. To replace equipment and keep pace with hardware technology, a lab must schedule major upgrades every 12 to 18 months. To justify these ongoing expenses to management, the lab manager develops a business case. A successful business case demonstrates how the lab mitigates risk by protecting intellectual property, trade secrets, and internal business plans from digital threats. From the steel walls and EMR shielding to the hardware write blockers and SHA-1 hashes, a digital forensics lab is built to provide an audit trail that maintains the integrity of the analysis and its results.